Good afternoon. Dear faculty opponent, dear members of the evaluation committee, dear supervisors, dear respondent, ladies and gentlemen, most welcome to KTH, the Royal Institute of Technology, and this Doctor's Defense. Today we will listen to the presentation of the thesis called Life Cycle Costing, Applications and Implementations in Bridge Investment and Management. And it will be defeated by Mr. Mohammed Safi. I will present the persons involved. Myself, I'm Johan Silverbrand. I'm professor in structural design and bridges at KTH. And the most important persons are the faculty opponent, Professor Jan-Erik Nilsson from the VTI, the Swedish Road and Traffic Research Institute in Linköping. The members of the evaluation committee are Professor Ann Landin from Lund University of Technology, Professor Lennart Elfgren from Luleå Technical University, and Professor Hans Lind from KTH. The supervisors are Professor Rait Karumi from KTH and Professor Håkan Sundqvist, KTH. The procedure is as follows. The respondent has roughly 30 minutes to summarize his thesis. Then I will give the floor to the faculty opponent who put his questions, and the respondent is supposed to answer these questions. During this time, no questions from the audience are allowed. This follows by questions from the evaluation committee, and then everyone in the room is free to put his or her questions. And then the process is closed here. The evaluation committee will have a meeting right after this meeting, and the rest of us will wait in the coffee room at the department for the verdict. With these words, I will give you the floor to the respondent. Please. One more issue. Please turn off your cell phones if you haven't done that yet. Mm-hmm. Now, it's yours.
Yes. Thank you very much. Welcome, everybody. I'm really very happy for seeing all of you here. Today, I will defend my PhD thesis, and the title, as you can see, it's Life Cycle Costing, Applications and Implementations in Bridge Investment and Management. I would like first to give a short background for my thesis. It's generally known that bridge investment and management involve selection from multiple alternatives. And this means that several technically feasible designs might be feasible for a certain bridge location or for repairing a bridge. And currently, conventional financial costing is guiding the agency's decision to implement a particular proposal. However, agencies nowadays are under severe pressure to optimize the use of taxpayers' money and ensure efficiency and sustainability of their decisions. That's why life cycle cost analysis is essential in bridge engineering, and it has a great saving potential. However, the interpolation and integration of life cycle cost analysis finding in bridge investment and management decisions is far from robust. And this is the main aim of my thesis, enhancing bridge investment and management decisions by robustly integrating life cycle cost analysis into procurement processes. And thereby, we can optimize use of taxpayers' money and ensure sustainability of our bridge infrastructures. And one other goal of the research is to develop convenient parameter and techniques for not only evaluating the bridge life cycle cost, but also user cost, aesthetic value, and environmental impact. And here I have my thesis, and it consists of two main parts. The first part is an extended summary, and it consists of 6 chapters. And the second part is appendices, consists of 5 papers, and I have Appendix B, Appendix A life cycle cost analysis tool, in which I clarifies all tools and methods I applied in my papers and thesis. And also I have Appendix B as recommended preliminary life cycle plans for the various bridge structural members compose the Swedish new bridges. And I have limitations in my thesis. The first thing is, when we consider the scope of life cycle costing, only options that fulfill the required functional demands are considered. Benefits for options that provide better function or enhanced functions are neglected. And the second thing, I mainly focused in project level decisions. And some of the results and conclusions are object specified. However, the proposed methods and technique could be applied for similar structures. Most of the techniques and methods developed in my research were designed to deviate with the established procurement procedure within the Swedish Transport Administration Trafikverket. However, bridge procurers and managers all over the world could adopt these methods and apply it for procurement and management of bridges and even other structures. In my research, I extracted and used data from the Swedish Bridge and Tunnel Management System called BATMAN to support my applications, and though other agencies could use data from their own bridge management systems. And also I have left some general parameters for policymakers and economists to decide on, such as the proper discount rate used in the analysis, as well as the willingness to pay extra for aesthetics and environment. And the other thing I would like first to clarify the definition of life cycle costing. And when we say life cycle cost, it's all cost incurred during the entire life of an asset or a product. And when we say about bridges, for example, we are currently designing our bridges to stand for 100 or 120 years. And during time, the first cost that we will pay is the initial investment cost when we inaugurate the bridge. And during time, the bridge needs to be inspected. And this will cost us money as well. And this is called inspection cost. And also we have to perform operation and maintenance after 1 year or every 2 years, for example. And also there will be, in some cases, periodically repair. And in many cases, we have to perform major repairs. And this is called major repair costs. And at the end of the life of the bridge, we will demolish the bridge and build a new one. So there will be also disposal cost. All of these are called life cycle measures cost. And the other important thing is when we perform major repairs, we need to occupy work zones. And the occupation of these work zones will disturb the traffic. So there will be indirect costs. And this cost will be incurred by the bridge user. And that's why it's called user costs. All of these are called life cycle cost. And the other thing is there is something called time value of money. And this can be explained by the cost that we will pay after 20 years. It's not equivalent or equal to the cost that we will pay today. And that's why we are using discount rate in the analysis. And the method for calculating all of these costs is called life cycle costing or life cycle cost analysis, LCCA. But it's really very important to acknowledge that the main objective of life cycle costing is the optimization or the reduction, the minimization of the total life cycle cost, not only the life cycle measures cost. And this means that the most cost-efficient bridge type is not necessarily being the one associated with the lowest life cycle measures cost or the longest lifespan. And the most life cycle cost efficient proposal is the one associated with the least equivalent annual cost, which counts for lifespan, initial investment cost, life cycle measures cost. And it's the function of the design style